Deep beneath most of Missouri's modern landscape is an ancient bedrock surface. Let's go find it.
Excuse me, can you tell me where the nearest billion-year-old bedrock is?
Well, there's some poking up about 150 miles that way down in the southeast Missouri.
Oh, I was really hoping for something closer.
Well, there is some about 2,000 feet away, but that fancy car won't get you there.
This has all-wheel drive.
Nah, you're gonna need a drill rig. They're about 2,000 foot straight down.
Anyone interested in Ozark geology has probably heard of the St. Francis Mountains, where Precambrian-era igneous rocks appear at the surface. Such exposures are rare in the broader region, and geology field trips drive in from many surrounding states to study places like Johnson's Shut-ins, Elephant Rocks, and Hughes Mountain. Almost everywhere else in the Ozarks, the rocks nearest the surface are much younger sedimentary rocks. But what's below them? In a previous video in this series on Ozark geology, we discussed how well logs help us study what's beneath the surface. Near this site in central Missouri, a deep drill hole went down about 2,000 feet, with a well log that recorded the drill's passage through recent glacial deposits and a thick sequence of sedimentary rock, before reaching much older Precambrian aged rocks at the base of the hole. Is this site special, or do such rocks lurk below elsewhere? We can use well log records to develop a three-dimensional understanding of regional geology, or at least a rough approximation of it. Here we'll be focusing on Missouri, because its well log records are more accessible than those in Arkansas, but the basic principles apply to the Arkansas Ozarks as well. As it turns out, Missouri well logs document around 900 locations where drill holes, mostly for mineral or oil exploration, have reached Precambrian rocks at various depths. Geologists commonly call these basement rocks because they generally lie at the base of the geologic sequence if you go deep enough. However, these should not be confused with the sort of basement rocks amassed by rockhounds. Both are interesting, and both can have an uncertain history. But in this episode, we're going to focus on the bedrock version through two questions. What makes these basement rocks distinct from those above them? And where and how deep are they distributed beneath the Missouri Ozarks? You've probably heard of the three basic rock types: igneous, metamorphic, and sedimentary. But geologists often simplify these into two categories based on their relative physical properties: hard rocks, igneous and metamorphic, and soft rocks, sedimentary. We'll go deeper into the specific composition of regional basement rocks in a later video. But for now, just understand that there's a distinct physical and age difference between the Precambrian-era hard rocks at the base of the regional sequence and the much younger Paleozoic-era soft rocks above them. By the way, if you need a refresher on geologic eras, check out our previous video summarizing the Ozark geologic timeline. If you had magic goggles that could penetrate all of Missouri's soil, river deposits, and Paleozoic soft rock, down to the hard Precambrian basement rock, what would you see? We did some 3D modeling to explore this question. For reference, here are the existing Precambrian surface exposures with a lot of vertical exaggeration for clarity. The white surface here represents sea level. Now let's introduce well logs. Each of these columns represents a well log that reaches Precambrian rock at its base, though in this view we're only showing their extent above sea level. So the tops of these columns represent the current land surface's elevation, again with a lot of vertical exaggeration. If we were to connect the tops of these, we'd have a very rough model of Missouri's modern landscape. But if we rotate this view further, we can see how deep these wells go beneath sea level. In this view, the base of each column represents the top of the Precambrian rock. This immediately shows that Precambrian rocks aren't found at consistent depths, but are instead pretty variable. So what would it look like if we took the bases of all these columns and extrapolated them into a surface? The result is a pretty cool visualization of the ancient Precambrian surface buried beneath modern Missouri, with the obvious caveat that this is a broad-scale model, limited by gaps in data, and not an exact representation. The roughly trimmed edges exclude areas with no data, including the boot heel of far southeastern Missouri, which is a special case that we'll cover in a minute. What we can see is a lumpy but roughly dome-shaped surface that separates the Precambrian hard rocks below from the Paleozoic soft rocks above. This surface reaches its highest elevation in the St. Francis Mountains, the center of a broader regional structure known as the Ozark Dome. This is part of the reason that the region's geologic map shows a concentric bullseye pattern. But beyond the Ozark Dome, there are other features of note. For example, the Precambrian surface drops away to the northwest, into what's known as the Forest City Basin, the opposite of the surface topography that slowly rises to the northwest. So what more do we know about the rocks forming this buried surface? Drill holes have provided direct samples of what's down there, and in the St. Francis Mountains we have the luxury of seeing volcanic rocks and granites at the surface. These are part of a broader collection of igneous rocks called the Eastern and Southern Granite Rhyolite Provinces, named for their composition. But to the north and west, the situation is more complicated. Basement rocks in these provinces include both igneous and metamorphic rocks. You can see this directly in the well log data. Here we've color-coded the type of rock found at the base of every drill hole. Igneous rocks dominate southeast Missouri, including both intrusive granitic and extrusive volcanic rocks. But as you go west and north, metamorphic rocks start appearing in the well logs, suggesting a distinct geologic history that's further supported by radiometric dating. The igneous rocks of the eastern and southern provinces date to a time span from roughly 1.5 to 1.3 billion years ago. By contrast, the combined igneous and metamorphic rocks to the west and north are older, having taken part in a previous mountain building event that incorporated even older rocks. So very generally across Missouri, Precambrian basement rocks are older to the northwest and younger to the southeast. But it's complicated. These provinces contain evidence of mountain building and volcanism, collectively spanning hundreds of millions of years of tectonic action. This tectonic activity contributed to the building of the core of North America, a region known to geologists as Laurentia. In future videos, we'll be talking about the younger sedimentary rocks on top of this Precambrian surface. For now, suffice it to say that there's a gap of about 1 billion years or more between the Precambrian rocks and the younger sedimentary rocks deposited on top. But what about the Boot Heel region of southeastern Missouri, where we don't have well log data reporting basement rock? That's because the ancient Precambrian surface drops off precipitously southeast of the St. Francis Mountains in association with the Reelfoot Rift, home of the New Madrid seismic zone that caused the famous 1811 to 1812 earthquakes that were felt across the continent. Here, over 4 vertical miles of sediment have accumulated, far deeper than is practical to drill, so other geophysical methods have been used to study this area's structure. Geophysical data show that the Precambrian surface here has something like 25,000 feet of buried vertical relief between the St. Francis Mountains and the depth of the buried trench. That's significantly more relief than Alaska's Denali, one of the world's tallest mountains from base to peak. So if you were to look southeast from the St. Francis Mountains, using your special soft rock penetrating goggles, beware of vertigo. We think it's fascinating that there's a Denali's worth of hard rock vertical relief buried beneath the Mississippi River. But beyond the neato factor, the depth of Precambrian bedrock has real scientific and economic relevance. The Ozarks have a long history of bedrock mining for valuable resources like zinc, lead, and iron, especially in and near the hard rock St. Francis Mountains. And rapid growth in green technology means a soaring need for minerals and other rare earth elements needed for solar panels, EVs, and lots of other modern tech. These have to come from somewhere, and there are already signs of heightened interest in the Ozarks from geologists looking for new domestic sources of these strategic resources. For just one example, consider Missouri's now-defunct Pea Ridge mine, originally exploited for iron but long known to contain deposits of highly valuable rare earth elements and other strategic minerals. The existing mine shafts extend well over 2,000 feet down through Paleozoic soft rocks to reach extensive ore deposits within Precambrian hard rocks, and could be reopened with the right incentives. In addition, a new study is investigating whether the mine's surface tailings could be reprocessed to extract now critical resources. So being aware of the depth and distribution of the Precambrian basement rocks beneath the Ozarks is quite relevant for complicated questions and tensions related to environmental, economic, and geopolitical considerations. These hard rocks will likely be at the center of some hard questions. They may be mostly buried, but they should not be overlooked. So as fascinating as all of this is, it still leaves a lot of questions. Like, what are the Ozarks' exposed Precambrian rocks actually composed of, and what do they look like on the ground? How did that buried Precambrian surface develop, and how has it changed over time? And why is there almost 1 billion years of missing time between those hard rocks and the soft rocks above them? We're sure you can think of other questions, which you're welcome to leave in the comments below. In the meantime, stay tuned for future videos as we continue this series about the endlessly fascinating geology of the Ozarks.